This lecture is titled Whatever Happened to Boundaries. It says everyone seems to be playing well within the boundaries of his usual rule set. I've yet to hear anyone say something that seemed likely to mitigate the idiocy of this age. So, one of the first things we want to look at is we want to say, okay, what happens whenever a wave hits a boundary? And there's multiple things that can occur. So, it says you should be able to identify the three major things that can happen when a wave hits a boundary. You should be able to identify the major wave vocabulary on a standing wave. You should be able to predict the frequency at which you can find harmonics, and you should be able to understand how harmonics are generated in pipes and strings. So, what we already knew, it says waves can reflect when they hit a boundary. Now, waves, we did this. You actually generated a slinky, a pulse wave, and it hit a barrier, and then it bounced back on the other side. So we know that waves can reflect. We learned that in the very first lab that we could do. And we actually found out that not only does it reflect, but it's actually dampened a little bit because the wave is actually smaller generally when it bounces back. Okay, what we learned in the lab this particular time says that waves can refract when they hit a boundary. Waves slow down when they enter different media, and they can also diffract. So there's a couple other things that waves can do. They can reflect, they can refract, and they can diffract. So the first one is reflection, and reflection says that a wave bouncing off a surface will bounce off at exactly the same angle, and this is called the law of reflection. Now, one thing that you should know is that the angle is actually measured from this line right here. This line right here is called a normal line. The reason why it's called a normal line is the same thing as 90 degrees, which is the same thing as perpendicular, which is the same thing as orthogonal. So what it means is you have a line that's 90 degrees to the surface, and that is where you measure the angle from. So theta I in this case is this right here, and theta R is this right here. Okay, the reason for that is there are mirrors that are actually curved, and whenever you have a curved mirror, you have to account for that as well. So you can't deal with that right now because you have to say, okay, I've got to measure from um, a common straight line, and so that's why we use the normal line as opposed to the surface. Okay, this basically says that if this is 35 degrees, this is 35 degrees. If this is 7 degrees, this is 7 degrees. If this is 20 degrees, this is 20 degrees. And that's the law of reflection. Okay, now reflection has a lot of uses. You use it looking in the mirror every day. Okay, whenever you look at the mirror, you see your own reflection in the mirror, and from there you can go ahead and say, yeah, that's me in the mirror. And if it shows me that, if the angles were different, you would look taller, you would look wider, you would look different. But because the angles are the same, that means that you look exactly like you should see yourself. Okay, next you have echolocation. Echolocation is what bats actually use to see. They send out sound waves that reflect off of surfaces, and when they come back, they can kind of see in the dark. We use the term see loosely because they're using sound waves, but they can detect where they are based on the reflection of those particular sound waves. Next, you have sonar, which is basically the same thing that ships do. They send out sound waves in the ocean. Whenever they send those out, they hit things and come back, and you can kind of generate a map. Another thing is fiber optic cables. Fiber optic cables actually use something called total internal reflection to bounce light signals back and forth in a wire and quickly move data from one point to another. Okay, a fiber optic cable is much more um, it's much faster than moving electricity down a wire or some sort of electrical current. There are two types of reflection that we need to talk about, with the first being what's called open reflection. Okay, open reflection is when you have kind of a movable barrier right here. So this right here is movable. And because of that, when the wave comes in along the top and it hits this movable barrier, the barrier itself, this ring kind of moves up, and then it generates the wave going backwards along the same side. So it's where a wave hits a boundary, in this case it's a pulse, hits a boundary, and it reflects back on the same side. What that means is that this barrier right here is movable. Okay, whenever you have that movable barrier, you generate open reflection. And so if we have open reflection, that means we probably have closed or fixed reflection as well. And fixed reflection is where you have a clamped or a rigid barrier. And that's what we actually had when we did the Slinky Lab to begin with. So you generate a pulse, and whenever you have the pulse, it's going to hit this particular side right here. But because this is stuck, what happens is the wave will actually invert. And when the wave inverts, then it will come back on the opposite side. And that's fixed reflection. Okay, so some example questions. It says, what is the missing angle? It says this is not drawn to scale. And so it says that this right here is a 20-degree angle. Okay, and so because of that, we need to use the law of reflection to figure out what this missing angle is right here. So here's how we're going to do this. We say, okay, well, that's 20 degrees. That means this must be 20 degrees. This right here is defined as the normal line. So the normal line is 90 degrees. Well, if this is 90 degrees here, and this is 20 degrees, that means that this must be 70 degrees. Okay, because 90 minus 20 is 70. Now, if you were to look at it, you have a triangle that's made. Okay, you see a triangle that begins right here. And so a triangle contains 180 degrees. You have one 70-degree angle, which is right here. You have one 40-degree angle, which is right here. And when you subtract those two things, you get 70 degrees. So what you see right here is you see that this right here is 70 degrees as well. Well, if this is 70 degrees, okay, that means that this has to be 20 degrees, which means this has to be 20 degrees, which means that this has to be 70 degrees. So the unknown angle is also 70 degrees. Now, you need to be able to do these because it's just the law of reflection in basic geometry. What you're looking for is the two angles have to add up to 90 on one side of a normal line. Whenever you form a triangle, it has to add up to 180 degrees. And then you look for different relationships between the two. So that right there represents example. Standing waves are generated by the reflection of waves, the reflection and interference of waves. What you do is you actually generate a wave pulse, and because it hits a fixed boundary, it bounces back on the other side, and you generate this standing wave pattern. Okay, this standing wave pattern is what we looked at when we did our lab this 2 times ago on velocity of the wave on the string. So the standing waves are generated by the reflection and interference of particular waves because they're in a confined space. So a couple of vocabulary terms that are associated with standing waves are harmonics. Okay, harmonics represent the number of bumps that you see. So this one right here has one harmonic. This one right here has two harmonics. This is the third harmonic, and so on and so on and so on. So you count the number of bumps, and the bumps we actually refer to are called the antinodes. An antinode is a bump or a point of maximum intensity on a standing wave. A node, on the other hand, is a point of no amplitude. Okay, no amplitude on a wave. There is always going to be one more node than antinode. So for example, here I have one antinode, I have a node here, and there is a node here as well. Okay, here I have two antinodes, so I have 1, 2, 3 nodes. Here I have 3 antinodes, so I have 1, 2, 3, 4 nodes. So these places right here, you can actually grab a standing wave right there at the node, and it will still generate this particular wave. It may cut out some of the rest of it, but you'll still see that one amplitude right there. So one thing that you need to realize is that harmonics need to be in an integer pattern. You can have 1, you can have 2, you can have 3, but you can't have 3 and a third, and you can't have 1.5. It's got to be a whole number integer pattern. So if we were to look at this, it says draw the fourth harmonic and label all antinodes, nodes, the amplitude, and the wavelength. So for the fourth harmonic, you have 1, 2, 3, 4 antinodes. 1, 2, 3, and this is not a great drawing, but you have 4 bumps right there. And then what you have is you have a line that cuts in between it. Okay, and it says label all antinodes and nodes. So I have an antinode, 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 and antinode. Label all nodes. I'm going to change it to a different color. Node, 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 and node. And if you look, I have one more node than I have antinodes. Then next it says it wants to do the amplitude. The amplitude is from this equilibrium line, or 1/2 the distance at the antinode. So you have the antinode is from the middle to the top. That right there represents the amplitude. And then finally the wavelength. And the wavelength represents any 2 antinodes. So you have 2 antinodes, that right there represents one wavelength. Or you could do these two, and you could say that represents one wavelength. Okay, or you could do these two and say that represents one wavelength. Okay, next it says example B2. It says harmonics are often called overtones, with the second harmonic being the first overtone, the third harmonic being the second overtone. It says what is the harmonic number, overtone, and number of antinodes in the picture below. So what we do is we say, okay, I have 1, 2, 3, 4, 5 antinodes. So since I have 5 antinodes, that is the fifth harmonic. It represents the fourth overtone, and there are 5 antinodes. You could also say that there are 6 nodes. Next, this is an extension. It goes a little bit beyond because it introduces a formula that's not on your formula chart. It says the harmonic number. So you have the frequency of the nth harmonic is equal to the harmonic number times the fundamental frequency. And the fundamental frequency represents the frequency at which you find the first harmonic, so in which you find one bump. Okay, that right there will allow you to look for any of the other frequencies with a pretty good degree of accuracy. So the fundamental frequency represents the cycles per second that's necessary to generate that. The harmonic number has to be a whole number, so it can be 1, 2, 3, 4, 5, etc. But it's a whole number integer. So let's say I'm looking for the fifth harmonic. I would take 5 and multiply it by whatever the fundamental harmonic was, say it's 10, and I would expect to find the fifth harmonic, 1, 2, 3, 4, 5. I think I drew the 5 there. I would expect to find the fifth harmonic at 50 hertz. So that's a relationship there. It's kind of a direct relationship. So once you find the fundamental frequency, you're in good shape trying to figure out the rest of it. Next it says the second harmonic is produced when the wave oscillates at 40 hertz. What is the fundamental frequency? So if you find the second harmonic when it oscillates at 40 hertz, so I have the frequency of the second harmonic is 40 hertz, and you have the harmonic number is 2, that allows you to solve for the fundamental frequency. Okay, you would say F2 is equal to 2, or our H number, times the fundamental frequency. So you'd have 40 equals 2 times FF. Divide both sides by 2, and what you get is the fundamental frequency is 20 hertz. In the next example, it says 20 hertz produces the fourth harmonic. What frequency would you expect to find the 10th harmonic? So the first thing that you need to do is you'd say, okay, I've got 20 hertz, and that's the fourth harmonic. So I would say 20 equals 4 times F of F. The fundamental frequency, therefore, must be 5 hertz. Once I've established that the fundamental frequency is 5 hertz, now I can say, well, 10 times the fundamental frequency is where I would expect to find the 10th harmonic at 50 hertz. Beyond reflecting, waves can also refract when they hit a boundary. So a boundary is really just where it changes mediums. And in this case, you have a medium changing from something to something else, and instead of actually bouncing off it, what you see is the wave can actually bend and go through it. And you can see this in two particular instances. So you see a wave here that when it hits a boundary, all of a sudden it bends and it curves a different direction. So you're changing the direction of the wave, and a lot of times it's really hard to see it when you see it in this particular setup. But it's a little bit easier when you say, okay, here is my wave. When my wave is there, all of a sudden it enters something else and it changes direction. That right there is the refraction. It's the bending of a wave as it changes from one media to another. Now the reason for that bend or that change is, remember, the velocity of a wave depends on the medium in which it travels. So here what you have is an object that is moving very, very, very fast, and then when it hits this medium, all of a sudden it slows down, and when it slows down it starts to bend towards this. Once again, this is called the normal line. So it starts to bend towards this normal line, and because of that, it's because it slows down, it bends towards the normal line, it can actually distort what you hear or what you see. So because of that, it's really important. It has a lot of uses and applications. Now we're going to talk about refraction a lot more when we talk specifically about light, because this is going to be really important for lenses. But basically what you need to know is that when it bends towards this normal line, it's because it's slowing down. And when it bends away from this normal line, like this, it's because it's speeding up. So, refraction does have its uses. It's useful in glasses. Your eye itself is refracts light, so you can get it, and your brain can interpret the signal. A lot of times, the shape of a glass is used to look like there's more liquid in there than there actually is. Restaurants use that a lot. Rainbows are formed by refraction, the bending of light. Prisms also use the refraction of light. So refraction is very, very useful. Example D1 says, what can you say about the velocity of the wave in the two mediums? So what we have is we have a wave that comes in here. If nothing happened, it would go straight through like that. Remember, it's changing from one medium to another. So if it bends toward the normal line, remember this right here is my normal line. If it bends toward the normal line, it's because it's slowing down. But it doesn't. It bends the opposite direction. So what we can say is that it is speeding up. So what I can say is that the velocity of the wave is faster in the second medium and slower in the first medium. The last thing we need to take a look at is we need to take a look at diffraction. Diffraction is the apparent bending or spreading out of a wave as it encounters an obstacle. So you can kind of see it right here where a wave comes and it hits an obstacle. And this particular obstacle has a little gap in there. And because of that little gap, what you see is you see the creation of another wave. Okay, you see the spreading out of another wave because the wave will actually bend around it and form a new wave as it gets through the barrier. Now, diffraction actually has a lot of applications as well. Okay, diffraction is used in diffraction gratings. Diffraction gratings are what astronomers use to see what different color lights come from different stars. It's actually used for X-ray diffraction. This is how they actually determine the structure of DNA as being a double helix. They created a crystal, and in that crystal they used X-ray diffraction to say, okay, this is what it looks like. And you may say, well, how do you get a double helix out of that? And it's because it's a top-down view. And so you can actually see the twisting around of the different layers from the top down there. And diffraction actually is going to have a lot of applications again with holograms. Okay, the generation of holograms requires that you kind of diffract light and make it look like it's a three-dimensional structure. So diffraction, when you have multiple slits, okay, more than one. So if I have a slit here and a slit here, what I'm doing is I'm generating basically two waves. And remember, anytime you have two waves, they can actually interfere with one another. And so the question says, well, what if I take these two slits and I move them further away from each other? What will you get? And the answer is, whenever you move those two slits further away, and provided that you have a screen that's far enough back, is you're actually providing more opportunity for these waves to interfere with one another. And as a result, you'll see a different pattern of light that appears on the wall. It says what wave phenomena is responsible for the diffraction pattern on the wall, and that would be the diffraction and interference of waves. So you have waves that diffract as they move through a boundary, and then you have the interference of those waves that produces the light dark, light dark. So this bright spot right here would be constructive interference, and then you have these dark spots in between that are a result of destructive interference.